Thank you. I'm Paul Bernstein, and I'm the moderator for this session on nutrition and AMD. We're already running 15 minutes behind, but hopefully we will finish so that we're not too late for lunch. And there are three speakers that we have today, and the first one is going to be John Barbur from the Henry Wellcome Laboratories of Vision Research, which is in London. And he will be talking not so much about carotenoids, but more on detecting the earliest signs of eye disease. So without further ado, I will have John start.
Thank you very much, Paul. Can you hear me from the back? Is the microphone working? Yeah, right? Okay, well, thank you. I would like to start by borrowing one of Liz Johnson's words to describe this meeting as being so energizing. It is indeed, and I would also like to thank the Howard Foundation for supporting this symposium, and certainly John Nolan and his colleagues for sort of organizing such a fantastic scientific program, and I do mean it. Last night I went through my slides and I saw the first slide and I was horrified because I realized I had to explain it. I will be concerned with aging, the topic that has been mentioned here so much, but aging specifically in relation to distinguishing the normal degradation of visual performance as a result of aging from changes which are caused by disease. It is a real sort of problem in early detection of disease. Now, what have I got here? Well, a colleague of mine developed AMD, and as you can see here, the accumulation of subretinal fluid in this OCT scan, and the effects of Avastin injections over 22 weeks, complete recovery of acuity. What you see here are the color thresholds. This is a signature for red-green as well as yellow-blue sensitivity. And anybody that is normal would have all these dots falling within this small region here. So these are the foveal data, and these are results obtained 8 degrees in each quadrant. The only interesting thing about this data is that these results were measured 5 years before AMD was diagnosed clinically using amsler-Greeton OCT. Now, 30 seconds on City University, because we are not normally involved in carotenoid studies. We trace our origins back to 1896, which is actually sort of only 80 years later than the Downing College here. And just look how elegant our students used to be when you compare them with what they look like today. They were also infinitely more serious. Now, the Applied Optics department was started in 1903. And I really would like to sort of link it somehow to Cambridge, but the only way I can link it to Cambridge is by accepting the fact that most of the research, in fact, improved and optimized what Sir Isaac Newton has already described so beautifully in his principles on optics, reflections, refractions, inflections, and colors. But having said that, I think that the work that was done over decades at City University has found its place in many departments of optometry and visual science throughout the world. Now, later on, late 1960s, 70s, the research activities have enhanced. We started the Applied Vision Research Center, and then later on in 2005, the Henry Wellcome Laboratories for Vision Sciences. The aim is to encourage fundamental research very much along the lines that we heard at the symposium, fundamental research which has clear clinical as well as industrial applications. These are the various people who contribute to the research activities at the Applied Vision Research Center. This short movie was made about 4 years ago, so they're all much older now. It's coming to an end, hopefully. Okay, now I know that my topic of research is actually quite different to what you've heard so far, so I would just like to make sure that I cover a couple of fundamental aspects of color vision so as to ensure that you can follow the rest of the results I have to present. So, however complex visual world is, and I like this particular photograph because it contains lots of contours and edges defined by both chromatic as well as luminance contrast. However complex the visual world is, it ends up as a two-dimensional image on the retina, and all the information is carried in spatial modulations of either intensity or spectral content. That's all the information we have in the two-dimensional retinal image. Now, as the light travels through the optics of the eye, changes in spectral composition, largely as a result of absorption by the lens and the macular pigment, and also the size of the pupil, which determines the level of retinal illuminance. It is the function of the photoreceptors in the eye, the four principal photoreceptors, to extract this information, both in terms of spatial modulations of intensity as well as spectral content. And these photoreceptors cover the visual spectrum, as you see here, and the signals generated are packed into vision information channels, and this information is then transferred to the LGN and the cortex. Now we have the color channels, the yellow-blue, which compare the long wavelength part of the spectrum with the short wavelength part of the spectrum, and signal yellow and blue. Then we have the red-green channel, which compares the middle wavelength with the long wavelength. And then we have the photopic luminance channel, which is probably the most important in terms of acuity, in terms of temporal vision. And this relies on the sum of signals from the long wavelength, red, and the middle wavelength, green photoreceptors. In the average eye, there are twice as many long wavelength cone photoreceptors as we have M-cone photoreceptors, and for every 100 LNM cones, you have one S-cone. Now, finally, at lower light levels, we have the scotopic sort of channel, which is actually extremely important. I would take issue with Billy Wooten's comment that we should ignore the scotopic sort of function. In fact, we have 120 million photoreceptors in the eye and only 5 million cone photoreceptors. And I can assure you that nothing would evolve with this number of rod photoreceptors if they would only allow us to see in the dark. In fact, they are extremely important at intermediate light levels, and even relatively high light levels, do not fully saturate rod photoreceptors. Now, very briefly, how do we quantify the sensation and the strength of color signals? Well, we can use test charts. It has been done for centuries. We can use tristimulus values and chromatistic coordinates, which are more informative but more difficult to understand. But very, very briefly, imagine that you have a patch of light like this on the retina. Then it will generate signals in the long wavelength, middle wavelength, and short wavelength cones. And suppose these signals are in the ratio 1 to 15 to 3. Now, if the light level, the spectral composition of the light changes, so as to get ratios of 15 to 3 to 1, then effectively you change the hue that you're going to see. And if you double these numbers, you still see largely the same hue. It's just that the actual patch looks brighter. So what it would be extremely useful would be to sort of have a system that allows us to indicate what the actual ratio is for the signals generated in the three classes of cone photoreceptors. And this is what the CIE XYZ system is. So although these values, XYZ, are not actually direct representation of cone photoreceptor signals, they are linear transformations, so they can be traced back to the actual cone photoreceptor signals. Now, we need 3 dimensions, but we don't really like to work with 3 dimensions. We like 2 dimensions, and therefore it's easy to normalize these. You lose the information on the absolute light level, the luminance, but you maintain the color information, and we end up with these chromatistic coordinates x and y, and we can plot y against x, as you see here, and every spectral power distribution that would cause a triplet of signals in the cone photoreceptors can be plotted as a point in this diagram. All the spectral colors plot along the spectrum locus, the yellows here, the blues there, the greens there, the reds here, and the grays are here in the center. And this is daylight. This is what it would plot. And what this graph shows here is a much enlarged contour, threshold contour, so that if someone needs to discriminate or to just detect a color change from gray, one needs to have a chromaticity change which is indicated here. You would have to go towards any point on this contour. Okay, now this is much larger than it is in reality. You will see in a moment. If you take a small portion of this ellipse, this is the daylight, and if you measure how far you need to go in each direction to just see a color, this is the median ellipse for 333 normal trichromats. Now, let me illustrate why this is so useful. This is the background. If you move away from the background in a particular direction like this, towards the red, for instance, okay, you take a point such as this one here, what you generate is a color. You generate a hue which remains relatively unchanged, but it becomes more saturated the further you go away. And what we can do is to take the spectral power distribution of the test target and that of the background and use the information about the sensitivity of the various photoreceptors to plot the contrast which this particular patch generates in each class of photoreceptor. And this is what it looks like. We plot here the cone contrast, including the rods, which is that function here, as a function of distance away from the background. So if you move further towards the spectrum locus, you get a larger and larger contrast, but just note that the actual ratios of this contrast remain largely unchanged, and that's what determines the hue. And the further you're away, the more saturated the color becomes. Now this is a very good measure, that distance, of chromatic sensitivity, of the severity of color vision loss, because the further you are away, the bigger the cone contrast signals that you generate. By the way, I don't mind having questions during the talk, but probably you don't prefer these. Okay, now, what is extremely interesting to really understand color vision is if you take every point on this ellipse, remember, it's the average for 333 normal subjects. If you take every point, and the way we do this is to take the horizontal as being 0 degrees, and then we measure this angle in an anti-clockwise direction. So that would be 90 degrees, that would be 180 degrees. And what we do is we plot the cone contrasts, the long wavelength, middle wavelength, and short wavelength cone contrasts as a function of direction. 0 and 360, they correspond to the same direction, which is this direction. Now, the reason why this is really revealing is because it tells you what gives you your color vision. Note that the red and the green cone signals cross at 0 for this particular angle and for that particular angle, and that is exactly sort of this direction. Any colors that are not along this direction are mediated by the red-green system, and as you can see here, the S-cone contrast is 0 here, so for that direction we have pure red-green stimulation. And we need 0.4% contrast for the long wavelength cones and about just under 0.8% contrast for the M cone photoreceptors to just discriminate red-green color differences. Now, these are sufficiently small so as to compare very, very favorably with our optimum achromatic contrast sensitivity. Now, note this particular point. When you see blue, for instance, in this direction, you only have S-cone activation. The L and the M stay constant. When you see yellow, you only have S-cone activation, but there's a decrement in S-cone signal. The L and the M stay constant. You need about 7 to 8% contrast, 7 to 8% contrast to just see yellow or blue, as opposed to 0.4 to 0.8% contrast to see red-green. And this is the reason why most studies have always concluded that the yellow-blue system is more effective in most diseases of the eye. Now, if we magnify this picture, you see things clearly. I should have done this earlier. And you see these angles here, 67 and 247, which is that axis, and 154 and 334, which is this axis. Now, these two axes are important because they label two different chromatic mechanisms, the yellow-blue and the red-green. Okay, now, how do we isolate the use of color signals? You have seen from my earlier slide that there are a number of different channels that would respond to anything that we image on the retina. And it's important to isolate the use of color signals, otherwise you will see the object by using luminance contrast. Well, we carried out a study on camouflage. Admittedly, it was done about 20 years ago for the Ministry of Defense, and those were the good times because they used to come to you, give you a massive grant, and never even expect you to write a report, and just trust that you were sufficiently interested to carry out the work. It was great because instead of using this kind of pattern, we investigated systematically how different stimulus attributes interacted with each other in the background and the test target. And what we discovered is that this kind of noise blocks out the detection of any luminance contrast defined motion, but it does not affect the color signal at all. And these form the basis of the CAD test, which you see here. And what we've got here are data, the statistical data for the 333 normal trichromats, namely the 2.5% and the 97.5% limits, which are indicated by the outer and the inner ellipse. And the black curve here shows the median sort of ellipse. And what we do is we take these major axes as a measure of yellow-blue threshold, and we label that as 1. And the minor axis as a measure of red-green threshold, and we label that as 1. So from now on, all the thresholds are expressed in terms of standard normal units. And what that means is if you have a value of 1, you're median. If it's less than 1, you're definitely better than the median standard normal. And if it's greater than 1, you need a larger signal strength. So if you have a threshold of 3, you need 3 times the color signal strength required by the median normal trichromat. And this is what the results look like. You see the normal observer, very good values. These green symbols here plot the results for a subject with congenital deficiency. Is the smallest minimal deficiency that we measured in about 500 color deficient subjects. And as you can see, the points fall outside the normal range for red-green, but they are well within the normal range for yellow-blue. And these are results for a severe proton-like observer. And finally, somebody here who's a dichromat, a subject who relies on L cone responses only, does not have any M cones. It is extremely easy to separate and diagnose the different classes of deficiency and also to label accurately those that have acquired color deficiency. Now, let me show you what the distributional result is within normal trichromats. What we've done here is to rank the thresholds in increasing order in 330 normal trichromats. And we've taken the mean value and the standard deviation of the distribution. And we've taken 330 samples, theoretically, from this distribution. And we rank those. And as you can see, they plot in a very similar way, which suggests that one can use a single normal distribution to describe the variability within normal trichromats. If you do the same thing for subjects with Dutan-like deficiencies, 269, we actually need 4 distributions. And the reason for it is because the actual residual separation between the L cone photoreceptors and the L prime, the variant long wavelength photoreceptors, which effectively render some color vision in subjects with Dutan anomaly, there are about 3 or 4 distinct values. And therefore, you require about 4 distributions to predict the data. Now, the case with red deficiency is simpler. There's only 2 distributions, well, just a few samples from a 3rd distribution here. The reason why I show you this slide is to show you that the loss of color vision is really continuous. You can hardly say that somebody's sort of severe or extreme protonomalous or whatever. It is actually almost a continuum. Now, this slide is very, very useful because it illustrates the relationship between yellow-blue thresholds and red-green thresholds for the normal trichromats, a value of 1 and 1, as you can see here. You see there's some correlation here between the two thresholds, and that's because of neural noise. And if you expand this region here, you see very clearly there's enough separation here to tell apart with no problem 100% sensitivity and specificity subjects with congenital deficiency from normal trichromats. And these are all subjects with either deuteranomaly or protonomaly, and these will be deuteranopes and protonopes. Now, using these techniques, there's absolutely no problem to either diagnose, to detect color vision loss, to separate congenital from normal subject, and to certainly describe and quantify the loss of chromatic sensitivity in any subject that has been clinically defined as having an eye disease such as glaucoma, age-related macular degeneration, diabetes, optic neuritis. Now, the problem is in fact different, and I'll come to that in a second, but let me just illustrate the kind of patterns that you get. Typical congenital deficiency, asymptomatic AMD, congenital and acquired, subject with diagnosed AMD, subject with diagnosed retinopathy as a result of diabetes, high intraocular pressure. As you can see here, the results are asymmetric, which is quite unusual. Finally, one of our students who, for some obscure reason, decided that he would like to track the sun for about 3 or 4 minutes. Now, let me show you this summary of results from various subjects with acquired color vision loss that passed through our labs over the last 6 years: firefighters, police officers, pilots. You see all the normals plot here. What we plot here is the yellow-blue threshold, 0 to 30. Remember that a normal value is 1. And the red-green threshold, 0 to 30. So all the normals plot here. If we have optic neuritis, you see very clearly that there's an almost equal red-green and yellow-blue loss. In diabetes, you see slightly greater red-green loss. In age-related macular degeneration, things are quite interesting because initially the yellow-blue loss is definitely larger. But then once you get transitions from the clearly dry phase to other phases, you tend to get an equal red-green, an equal increment in the red-green and yellow-blue loss. Congenital deficiency can produce this increased red-green loss, as you see here. But then look at this last slide. We have these crosses here, which plot subjects that happen to pass through the lab, referred to us by different hospitals or doctors. And we have no idea what they have. There's no clear clinical sign as to what their condition is, but they have significant losses of color vision, and they're definitely not congenital. Now, the original study that we carried out was really for aviation, and pilots, just like football players, they're very keen to do well. They usually retire by the time they get to the age of 55. They make sufficient money to actually retire, so we concentrated mostly on younger subjects, as you can see here. The experiments were done binocularly, okay, under optimum conditions. And as you can see, the red-green threshold plotted as a function of age, and the yellow-blue threshold plotted as a function of age. And as you can see from these results, I hope they're quite clear, there's virtually no correlation with age, so we can really be quite happy if I only had this set of data that age would not really affect, normal aging would not really affect significantly color vision. But then later on, we decided to extend the studies and to carry out the measurements monocularly when the thresholds are actually larger, significantly larger than they are binocularly, and also to increase the age range to 79 years of age. And all these points here that fall outside the normal range, they actually tilt this, they increase the gradient of this line, and as you can see here now, we have a correlation. Now, this is of great interest because we would like to use these tests to detect changes in color vision which are indicative of disease as opposed to normal aging. But how do we separate the effects of normal aging from disease? The same kind of picture we have for yellow-blue thresholds. Now, just as I said, we would like to know normal aging limits in relation to loss of red-green and yellow-blue chromatic sensitivity. Now, we know that color vision might be affected, vision in general, by changes in the optics of the eye, changes in the retina, changes along the visual pathways, and that these changes are caused by aging, systemic or eye diseases, and also toxicity effects, so for that matter, sort of lack of appropriate diet. Now, once the subjects are above 50, above 60 years of age, there is much increased variability, and this makes it very difficult to judge what is normal aging and to separate normal aging from slowly progressing diseases of the eye. Now, what we noticed is that when we drop the light level, normal subjects tend to have an increased threshold. But then we also noticed that subjects that had early stage AMD, or for that matter, subjects that were suspected to have to develop AMD, they tended to have a higher rate of increase in threshold as you drop the light level. So we asked ourselves if there's any way in which we can extract we can capture this bit of information from the dark, as it were, something that is known to ophthalmologists all over the world. It's if you give a patient a newspaper and turn the lights down, they'll find it very difficult to read the text if they have early stage retinal disease. So what do I mean by this? Suppose we measure the color thresholds, but now we vary the retinal illuminance. And you can get this pattern of results. Okay, that would be red-green and yellow-blue. And in another 56-year-old patient, we can get this pattern of results with a much more rapid increase and higher thresholds. So can we capture this information and put it into a single index? In other words, both the optimum threshold as well as the rate at which the threshold increases as you lower the light level. Now, we've got to take into account the effects of the optics of the eye, and we know from many studies, these data are from Van Noren and von Kratz, or von der Kratz paper, and they show the effects of aging on the transmittance of the lens. I reference these results to a 20-year-old, and of course you add the macular pigment, you can see a significant absorption of short wavelength light, so we need to take this into account. We do this using the MAP test, which was described by Dr. Rodriguez Carmona in her poster. It does have the advantage of producing the spatial profile of the macular pigment, but it also produces a measure of the spectral absorption of the lens for the blue light that forms the test component of the MAP test, and also produces a measure of the subject's rapid flicker sensitivity. The frequency is fixed at 17 Hertz, this is also extremely useful factor since it increases significantly in all the subjects. So we can use these bits of information, okay, the measured lens optical density as a function of age, the pupil diameter, the average pupil diameter during the test, which is measured using the P-scan system, and we can then use these parameters to correct for the light levels on the screen. The light levels are fixed for everybody, 2.6 to 65 candelas per meter squared, okay, but the corresponding sort of retinal illuminance will be affected by all these factors: macular pigment, lens absorption, pupil size, and we can convert the screen luminance to retinal illuminance in trolens. It's not an exact sort of computation, but we get a measure which is much more closely related to what we actually got on the retina. And as you can see, it does matter. If you take the subject, with that correction, all these points will be at the same location here, and with correction, the points are shifted towards the left because the light level reduces on the screen. Now we take all the subjects that participated in the study, about 50 subjects, all normal subjects, And we fit this particular function, and this is an extremely useful function because it's simple. The T0 here represents the best threshold that you get here, and the parameters k and alpha determine how rapidly the thresholds increase as you lower the light level. So this is the subject's threshold as a function of retinal illuminance E, and that's for red-green discrimination, and this is for yellow-blue. Then what we do is we take every subject and we fit this function. Then we calculate the area under the function, and again, I like this function because it integrates with no problem, so we even end up with an analytical expression here that gives us the area under the curve for the normal subjects, for the group of subjects investigated. So we have the mean area, if you wish, and then we can take any single subject and we can also calculate the area for the subject, and then we can define this health of the retina index as 1 minus the ratio of the area of the subject divided by the median sort of value. Now, what does this do? If these two values, if these two areas equal, that means that the HR index is 0, so that line here would correspond to this one. If this line is below, okay, the median, then we end up with a positive value here, so it's a positive HR value. And if this value is larger than the median, then we end up with a negative health of the retina index. Then what we've done is repeated the procedure for yellow-blue, and then what we do is we go through every subject and we compare them with respect to the median. And we end up with this distribution of the health of the retina index for red-green and yellow-blue threshold detection, and we extract the 2 sigma limits. It's not a symmetric distribution, but we use the probability density values that would correspond to a normal distribution. So we move along until we end up with the correct value here, the median and the 97.5 value. And as you can see, the distributions are quite tightly packed. Okay, the spread is limited. Then what we do is we go back and plot the HR index as a function of age. This is for red-green threshold detection. And now we add the 2.5 and 95% limits here. And as you can see, the majority of subjects fall within the normal range. The correlation is extremely small. There's effectively no effects of aging. Okay, but these subjects fall well outside the normal range, and so does this subject here for yellow-blue, I'll show you in a second, which is represented by a black diamond there. So we end up with a much tighter distribution, which clearly identifies those that are outside the normal range. And similarly for yellow-blue threshold detection, with this particular subject here, diagnosed with optic neuritis, this subject was tested after recovery from optic neuritis, and there is an HR index which is well outside the normal range for yellow-blue, but the HR index for red-green is actually within the normal range. And I think this is simply because there is recovery quite often in optic neuritis, and the red-green system somehow has recovered better than the yellow-blue. So we have the outliers clearly identified. So really, in conclusion, when we take into account the reduction in retinal illuminance, which is caused by short wavelength absorption of light, pre-receptoral absorption, as well as pupil size, okay, aging has only a very small effect on both red-green as well as, a very small effect on the HR index, okay? And this is of advantage since it identifies very clearly subjects that fall outside the normal range. Now, these are my final conclusions. So the new HR index captures the loss of chromatic sensitivity, but it also captures the rate at which this sensitivity worsens as the light level on the retina decreases. And I think that capturing this extra bit of information, okay, is extremely useful in terms of diagnosing changes in performance or classifying changes in performance as being attributable to normal aging or to disease. I think I just about summarized everything. The advantage of using this approach, as opposed to just measuring the color thresholds, is that the actual spread in HR values is narrower, and it identifies more clearly those subjects that fall outside the normal range. Now, as the results here indicate, a small number of subjects, usually over the age of 50, okay, have HR indices that fall outside the normal range. And it would be extremely interesting to sort of extend these studies to establish the extent to which these subjects will sooner or later develop diseases of the eye, as we have sort of demonstrated in the case of 3 or 4 subjects quite fortuitously that passed through our lab, which would suggest that we can sort of detect functional changes well before we have any clinically recognizable sort of signs. The last slide, but probably equally important, I would like to thank my colleagues, clinical colleagues, particularly Shobha Sivaprasad and Rupa Vemala, our research student, for contributing significantly to this study, Dr. Gordon Plant from the National Hospital London, Chris Canning from Moorfields Dubai Eye Hospital, and Marisa Rodriguez Carmona, Evgenia Constanta Corpolo, Alistair Hallow, and Matilda O'Neill from City University. So thank you very much, and I welcome questions and comments.